Alright, so today's topics is going to be on prefix sums, which is generally a silver topic in Yusaku contests. So let's get into what prefixes are. Prefixes are intervals of array that can be described as from 0 to an index a, where a is less than the length of the array. And there's also suffixes, which are essentially the opposite, where the interval starts from a and goes all the way to the last element of the array. And both prefixes and suffixes are more or less synonymous, and most of the time you can use either one or the other. And so what's important to know is that all prefixes can usually be computed using one loop. In other words, n prefixes can be found in O of n. And that's using kind of a DP-like idea to build each prefix. And I'm going to get into what DP exactly is in a future video, but for now, just bear with me here. And one benefit of prefix sums is that not only are they very powerful, but they're also very easy to implement. So let's look at a problem. Given an array of length n and q queries, each described as two integers a and b, such that q is equal to the sum of a subarray starting from a and ending at index b. Find an O of n solution. Now the brute force strategy, of course, is to loop through every query and find the sum, and loop through again and again and again. Well, that's too slow. Say if n was 1,000 and q was 1,000, then you're going to have to do a million operations, which is obviously not that bad, but let's say if n was like 100,000 and q was also 100,000, then it would get way too slow. You would need to find an O of n solution. And this is where we can use prefixes. With prefixes, we can calculate the intervals of a sum that go from 0 to any index a. And then we can subtract prefix at b minus prefix of a to get the total sum between a and b. And here's a snippet of Java code basically showing how to actually implement a prefix array. So you can see we initialize the first value, and then for every value after that, we build it upon the element within our input array and the previous element in our prefix. And so I'll walk through how to actually use this very shortly. So let's look at this past problem. And yeah, I'll just let you get to this website, and I'll talk about how to work this problem on my IDE. And so before we work on that problem, here's like a few more practice problems that you can also look at. All of these will be down in the description below. So yeah, that's cool. All right, so back to our coding part. As you can see, I coded up a brute force method for this problem. So I'm just going to walk through it a little bit. So as you can see, this is just reading in all the input. And then after that, we set an array list of results. And as you can see, we're just basically brute forcing this by starting from the back, and then when we want to find the lowest score to remove from that certain interval, we just loop through that interval and then find the lowest score there. And then we just calculate the average and so on. And as you can see, this is an O of n squared algorithm because of these two loops over here that can go up to n. And so based on these bounds, when n is less than or equal to 100,000, O of n squared should not run in time. And let's confirm that right now. So just waiting. First few cases should be fine. But yeah, test case 6 is already quite slow. And as you can see, we're starting the timeout. So obviously we have to implement some sort of optimization for this problem. So let's just wait for the rest of it to finish grading. And yeah, so as you can see, cases 7 through 9 all timed out, and we don't want that to happen. We want to create a better algorithm for this. And so the optimization we make is rather than finding the lowest score every time we create this new interval, we should pre-compute all of our lowest scores as prefix sums. And so the way to do that is over here. So this is the same problem, except I've implemented a prefix where we can keep track of all low scores. And so down here, rather than having to loop through all low scores, all I have to do is simply call low score at index I, and that will retrieve it. So how did I even calculate this low score in the first place? Well, this is where the magic happens. So low score array is more or less our prefix array, and buff is just kind of an initial value that we set at a high value, and this basically keeps track of the running minimum. So in other words, if this buff is greater than our current element starting from the back of our input array, then we set it equal, because we want buff to be the minimum possible value. And then we set low score at I equal to buff. And so as I moves along through this for loop, buff will decrease in value, and that will give the lowest value from low score at I, which we can call later on in here. And so basically this saves a factor of n, and because we have, instead of having a nested loops, we have two loops over here. This is an OMN algorithm. And so let's confirm to see if this runs in time or not. So as you can see, all cases ran in time, and it's pretty fast as well. The slowest test case is roughly, it's not even half a second. So with that in mind, one thing to take away from this lecture is know when to use prefix sums to optimize your code, because as you can see, the optimization in itself wasn't really that complicated at all. All we did was basically more or less modify this for loop and then move it outside of the outer for loop, so that we can just solve for all the low score values in one array rather than solving each one individually. And so yeah, as you can see, there's all 10 cases, and I'm going to, and yeah, so that's more or less, that's about it for this video. Let me know down in the comments what you think about it, and yeah, I'll see you all next time. Bye.